Hey everyone, and welcome to another deep dive with us. Today we're going deep underground to unlock the secrets of rocks and how they impact something that's pretty vital to all of us, energy production.
We're going to be diving into the world of petrophysics.
Petrophysics now.
Yeah, petrophysics.
It sounds...
It sounds complicated, but really it's just the science of understanding rocks and how fluids like oil, gas, and water flow through them.
Okay, so we're talking about the rocks that hold the oil and gas that power our world.
Exactly. And we're going to be focusing on how this all ties into hydraulic fracturing or fracking, the technique used to extract those resources.
Okay, so fracking. Got it. And what are we using to guide us on this deep dive?
We've got a chapter from a book all about it, ready to spill all the secrets. It's like we're about to become rock detectives.
I love that, rock detectives. So where do we even begin with something like this?
Well, this chapter really zooms in on how those rock properties are used to design these like super precise fracking operations.
Okay, so we're not just cracking rocks open randomly. There's a real science to it.
Oh yeah, definitely. It's pretty amazing when you think about it. I mean, we're talking about like manipulating things miles beneath the surface, you know?
That's wild. Okay, so the first thing that jumped out at me was this idea of well logs. They're like a window into the underground world, right?
Exactly.
So what exactly is a well log?
Well, imagine a series of measurements taken along the well bore.
Okay, like a probe going down and taking readings at different depths.
Right. So as the probe goes down, it gives us a glimpse into the different layers of rock and all their properties.
Okay, so each log is like a different test, revealing something different about the rock.
Exactly. Like one might measure how dense the rock is, while another measures how fast sound travels through it.
Fascinating. Now, the chapter mentioned that these well logs are essential for designing those hydraulic fracturing treatments.
Oh, absolutely. They are, because you see, we can't measure all the things we need directly.
Okay, so what kind of information are we getting from these logs that's so crucial for fracking?
Things like how much stress the rock is under.
Stress, meaning like how much pressure it's experiencing from the weight of everything above it.
Exactly. That's what we call in-situ stress. And the logs can also tell us how stiff the rock is, what we call its modulus.
So we're talking about how much the rock will deform or break under pressure.
Exactly. All crucial information when you're trying to create fractures in a controlled way.
Right, because you don't want those fractures going off in some random direction.
Definitely not. We want to be very precise about where those fractures go and how far they extend. Imagine trying to like create a tiny crack in a concrete wall, but you can't see the wall and you're doing it from miles away. That's kind of what we're doing here.
That is a wild thought. Okay, so I'm starting to see why those, well, the logs are so crucial. But before we dive into the specific types of logs, there's one thing in the chapter that kind of threw me off. It's this idea that even something as seemingly simple as depth isn't always so straightforward.
Ah, yes. You see, the way we define fracture height can actually change depending on the direction of the rock layers. It's like,
Wait, so the depth of a fracture can change depending on which way it's pointing?
kind of, yeah. Think about a slanted layer cake. You might measure the height of the cake from top to bottom, right?
Right, from the frosting to the bottom layer.
Exactly. But the actual thickness of each layer, well, that depends on the angle of the slice. You could get very different measurements depending on where you cut it. That's kind of what's happening here. The rock layers are often tilted or folded, so a fracture might be a certain length when measured straight down, but a different length when measured along the slant of the rock layer.
That's pretty mind-boggling when you think about it, that our perception of depth changes based on the orientation of these underground layers.
It's all about perspective, and it really highlights the importance of being very precise with our measurements and calculations when we're talking about fracking.
Right, because even a small miscalculation could have big consequences down there.
Exactly. So we have to be really careful about which depth measurement we're using, because it impacts how we design those fractures.
Okay, so depth is more complex than it seems. Got it. Now let's talk about those, well, logs in more detail. The chapter mentioned a bunch of primary logs, each revealing something different about the formation. What's the first one on our list?
Well, the first one that comes to mind is the gamma ray log, or GR log for short. It's basically a rock identifier, you could say.
A rock identifier, meaning it tells us what kind of rock we're dealing with.
Right. You see, different rocks emit different levels of natural radioactivity.
Really? Rocks are radioactive.
Well, in a natural sense, yes. It's not like they're glowing in the dark or anything.
Okay, good to know. So this gamma ray log measures that natural radioactivity.
Exactly. And because different rocks have different levels of radioactivity, we can use this log to map out the different rock layers down there.
So, like, we could tell if we're looking at a sandstone layer versus a shale layer, for instance.
Precisely. And that's important because different rock types will behave very differently when we're trying to fracture them. Like, sandstone's going to be much easier to fracture than a hard, dense shale.
So this gamma ray log is kind of like our first step in understanding the underground landscape.
You got it. It's like creating a map of the different rock layers before we start digging in.
Okay, so we've got our rock map. What's next?
Well, next up we've got the density and neutron logs. Now these two, they work together as a team.
Oh, how so?
Well, they tell us about the porosity of the rock.
Porosity. Refresh my memory on what that means again.
Porosity basically means how much empty space there is in a rock. Think of it like a sponge, you know?
Okay, so a rock with high porosity has lots of little holes or spaces within it.
Exactly. And those spaces are important because they're where the valuable fluids like oil and gas can hang out.
Ah, so it's not just about breaking the rock. It's about breaking it in places where there's actually something to extract.
Exactly. Now the density log, that one uses gamma rays.
Again with the gamma rays.
Yeah, but this time they're used to measure how dense the rock is.
I see. So a really dense rock would absorb more of those gamma rays.
Precisely. And a less dense rock would let more of them pass through. And the neutron log, well, that one estimates the amount of hydrogen in the rock.
Hydrogen. What does that have to do with porosity?
Well, hydrogen is found in fluids, you know.
Right, like water and oil.
Exactly. So a high hydrogen content can suggest higher porosity, meaning there's more space for those fluids to be present.
Okay, so we're basically using these two logs to get a sense of how much fluid is likely to be trapped within the rock.
That's a great way to put it. And that helps us target zones where those fluids are more likely to flow once we create those fractures.
Got it. Now, the chapter also mentioned temperature logs. Seems pretty straightforward, but why is temperature so important down there?
Well, temperature can play a big role in how those fracking fluids behave, you know.
Really? So the temperature deep underground can affect the fracking process.
Absolutely. Different fluids react differently at different temperatures. Some might become too thick or viscous, while others might break down or become unstable. So knowing the temperature down there, well, that helps us choose the right fluids for the job.
It's like choosing the right oil for your car engine. You wouldn't put thick, heavy oil in a tiny, high-performance engine.
That's a great analogy. We need to make sure the fluids we use down there can handle the heat and pressure.
Makes sense. Okay, on to the next type of log. The chapter mentioned something called sonic logs. And I always think of these like listening to the earth. It's like how you can hear the difference when someone walks on hardwood versus carpet, right? Different materials, different sounds.
I like that analogy. You're spot on. Sonic logs use sound waves to measure how fast sound travels through the rock. And believe it or not, that speed can tell us a lot about how stiff the rock is.
Stiffness, like how much it resists bending or breaking.
Exactly. We call that stiffness Young's modulus, or E.
Okay, Young's modulus, got it. So the faster the sound waves travel through the rock, the stiffer it is.
Precisely. Think of it like this. Sound travels faster through a stiff material like steel than it does through a softer material like, say, rubber.
Right, that makes sense. So we can figure out how resistant the rock is to breaking just by listening to it. Pretty cool.
It is pretty cool, and it gives us a way to estimate how much force we'll need to apply to create those fractures.
But hold on, the chapter mentioned something about dynamic versus static modulus.
Yeah.
Why do we need to differentiate between those two?
Ah, that's an important distinction. So the dynamic modulus, that's what we get from the sonic log.
And it's a measure of how stiff the rock is under those really fast conditions of the sound wave, right?
Exactly. But when we're fracking, we're applying force over a longer period.
So it's more of a sustained pressure rather than a quick pulse.
Right. And the rock's stiffness under those slower conditions, that's what we call the static modulus. And that's what we really need to know for designing our treatments.
Ah, so it's like the difference between tapping something lightly and pushing on it steadily. The way it responds could be totally different.
You got it. We need to make sure we're using the right modulus for the right situation.
Okay, that makes sense. Now, the last type of sonic log the chapter mentioned was the dipole sonic log. It measures something called shear wave velocity. Can you explain what shear waves are and why they matter?
Shear waves. Well, imagine you're shaking a rope up and down. That wave traveling along the rope is a shear wave.
So it's a wave that moves side to side rather than forward and backward.
Exactly. In rocks, these shear waves can tell us a lot about the stresses that are already present down there. You see, the speed of those waves is affected by those stresses, and by measuring how fast they travel, we can get a better understanding of the forces pushing and pulling on the rock.
So it's like the Earth is already whispering to us about those stresses if we know how to listen.
I love that. You're exactly right. And knowing those stresses, well, it's crucial for planning those fractures. We need to know how much force to apply and in which direction to make those fractures grow the way we want them to.
Right, because we're trying to work with those natural stresses, not against them.
Exactly. Too much force and we could create unintended fractures. Too little and they might not grow far enough. It's all about finding that sweet spot.
Okay, so we've covered gamma ray, density, neutron, temperature, and sonic logs. That's quite the toolkit for understanding these rocks.
We're becoming quite the rock detectives.
We are. But before we move on, I'm curious, are there any pitfalls we need to be aware of when interpreting these logs? It seems like there's a lot of room for error if we're not careful.
That's a good point. One thing to keep in mind is that these logs, they're just measurements, right?
Right, they're clues, but we still need to use our brains and our knowledge of geology to interpret them correctly.
Exactly. It's like having all the pieces of a puzzle but not knowing how they fit together. We need to use our expertise to make sense of the data.
And are there any specific examples of how these logs might mislead us if we're not careful?
Well, for example, the chapter mentioned that temperature logs might not always give us the true formation temperature.
Oh, how so?
Well, things like how long ago the well was drilled can affect those readings. If the mud used to drill the well hasn't had enough time to cool down, the temperature log might show a higher temperature than the actual rock formation.
Ah, so it's like taking your temperature right after a workout. You might get a reading that's higher than your normal body temperature.
Exactly. We have to take all of that into account when analyzing the data.
So it's not as simple as just reading the numbers off the log. There's a lot of nuance and interpretation involved.
You got it. It's like being a detective. You have to consider all the evidence, not just the obvious stuff. And speaking of evidence, I think it's time we go a little deeper into how those density and neutron logs work together to give us that porosity information.
Yes, let's dive in.
Remember how the density log uses gamma rays? Well, those gamma rays actually interact with the electrons in the rock.
Electrons, like the tiny particles that whiz around the atoms.
Precisely. The more electrons there are, the denser the rock. So a high density reading on the log means we're likely looking at a solid, compact rock with fewer spaces for fluids.
Okay, so it's all about how much those gamma rays get absorbed by the rock.
Right. Now, fluids like oil and water, they have fewer electrons than solid rock. So if the density log shows a lower reading, it could indicate a higher porosity, meaning more space for those fluids to be present.
Ah, so it's like the density log is giving us clues about the composition of the rock, not just its density.
Exactly. And we can use that information to infer whether we're likely to find oil or gas in those porous zones.
Now, I remember you mentioned that the neutron log is all about detecting hydrogen. How does that work?
Well, those neutron logs, they send out these bursts of neutrons into the formation, and those neutrons, they love to interact with hydrogen atoms.
So the more hydrogen there is in the rock, the more those neutrons will bounce back to the detector.
You got it. And since hydrogen is a key component of both oil and water, a high hydrogen content can also suggest higher porosity, meaning more space for those fluids to hang out.
So both the density and neutron logs are looking for signs of those fluids hiding within the rock, but they're doing it in different ways.
Exactly. And by comparing the readings from these two logs, we can get a pretty good idea of the overall porosity of the rock.
It's like getting two different perspectives on the same scene, each revealing something unique.
I like that. It's all about piecing together the clues to get the most accurate picture of what's happening down there.
Well, I'm definitely starting to see the bigger picture. But before we go any further, I think we need to take a quick break. We'll be back soon to delve deeper into those fascinating well logs and explore how they help us unlock the energy trapped beneath our feet. Stay tuned.
Sounds good. And you know, sometimes when we plot the density and neutron log readings together, they do something really interesting.
Oh, what's that?
They cross over each other.
Crossover. What does that tell us?
It can tell us a lot, actually. Sometimes it's good news, sometimes it's a bit of a warning sign.
Okay, I'm intrigued. Give me the good news first.
All right, so picture this. The density log shows high porosity.
Right, meaning lots of space for those fluids.
Exactly. But then the neutron log, it shows low porosity, like not as much fluid as we'd expect based on the density reading.
So the two logs are giving us conflicting information
Yeah, and that's the clue. That opposite reaction, as we call it, that's often a strong indicator of gas presence.
because gas is less dense and has less hydrogen than oil or water.
Exactly. So it throws off those readings in a very specific way. That's our treasure map right there.
So this crossover effect is like a secret code telling us where the good stuff is.
Exactly. And here's the thing. That same crossover effect can also alert us to potential traps or zones that we might want to avoid fracturing.
Okay, so what kind of trap are we talking about here?
Well, sometimes the opposite happens. The density log might show low porosity, suggesting solid rock, but then the neutron log shows a surprisingly high porosity. This often means we're dealing with a clay-rich zone.
Clay. But clay can hold water, right? Doesn't that mean there's space for fluids?
Well, here's the catch. Clay minerals bind a lot of water within their structure.
Ah, so the neutron log sees all that hydrogen for the water and thinks, hey, there's a ton of porosity here.
Exactly, but that water, it's not actually available for oil and gas to flow. It's like a mirage in the desert. Looks promising from a distance, but when you get closer, there's nothing there.
So it's like a false promise of porosity. Looks good on the log, but doesn't actually deliver when it comes to fluid flow. So we need to be careful about those clay-rich zones. And that's where those gamma ray logs we talked about earlier come in handy, right?
You got it. Remember, gamma ray logs can detect those shale layers, which often contain a lot of clay. And shales, well, they're notorious for being less permeable, meaning fluids don't flow through them easily.
So by combining those gamma ray readings with this density-neutron crossover information, we can get a much clearer picture of where to focus our fracking efforts.
Right. Precisely. It's like having a detective's toolkit, right?
Yep.
We're using multiple clues to solve the mystery of what's going on down there.
I love this analogy. But before we move on to the next clue, I'm curious, are there any other types of logs that help us identify these potential traps or barriers to fracture growth?
Well, sonic logs can also give us some hints. Remember, they measure how fast sound waves travel through rock, right?
Right, and that tells us about the rock's stiffness, its Young's modulus.
Exactly. And those sonic logs can also help us identify zones that might be particularly challenging to fracture.
Challenging, meaning they're super strong and resistant to breaking.
Right. You see, different rock types transmit those sound waves at different speeds, and those speeds can tell us something about the rock's mechanical properties, basically how it responds to stress. Some rocks are just naturally more resistant to breaking than others, you know?
Makes sense. So we need to be aware of those tougher layers because they could act as barriers, preventing our fractures from growing as we'd like them to.
Precisely. It's like trying to drive a nail through a piece of wood but hitting a knot. It's going to be a lot harder to get that nail through, so we want to avoid those knots in the rock if we can.
Okay, so we're not just looking for porous zones, we're also making sure those zones are frackable. We want those fractures to grow nicely and reach as much of the reservoir as possible.
Exactly. We're trying to create those pathways for the oil and gas to flow. And we need to make sure those pathways are open and accessible.
Okay, so sonic logs can also help us with that. Now, the chapter also mentions something about using sonic logs to calculate specific mechanical properties of the rock, like Young's modulus and Poisson's ratio. I vaguely remember those terms from physics class, but could you give me a quick refresher on what they actually mean?
Sure. So Young's modulus, we've already touched on that, right? It's a measure of a rock's stiffness. Think of it as how much it will deform or stretch under a given amount of stress.
Okay, like a rubber band. A stiff rubber band has a higher Young's modulus because you need to apply more force to stretch it.
Exactly. And a rock with a high Young's modulus will be harder to fracture. Now, Poisson's ratio, that one's a bit trickier to visualize, but it basically describes how a material changes shape when it's squeezed or stretched.
Okay, so if you squeeze a rock in one direction, Poisson's ratio tells you how much it will bulge out in the other directions.
Exactly. Some materials, when you squeeze them, they tend to get thinner in the direction you're squeezing and wider in the perpendicular direction. That's a high Poisson's ratio. Other materials, they might not change shape as much, meaning they have a lower Poisson's ratio.
Okay, I think I'm starting to get it. So these properties are essentially telling us how the rock will behave when we start pumping those fracking fluids into it, right?
Precisely. We need to know if it'll crack easily, how those cracks will propagate, and whether they'll stay open or tend to close back up.
So it's all about predicting how the rock will respond to the fracking treatment.
Exactly. And those mechanical properties, they're key to designing a successful operation.
This is amazing. It seems like we're getting pretty good at figuring out what's going on down there. But I'm curious, is it always this clear cut? Are there any times when these logs might give us misleading information?
Well, you know those sneaky gas molecules we talked about earlier? Those can sometimes throw a wrench in the works.
Oh, how so?
They can actually mess with our density and compressional velocity readings, making it look like the rock is less dense than it really is.
Ah, so gas can create a sort of illusion on those logs.
Kinda. But don't worry, we have ways to deal with that. We can mathematically adjust those readings to account for the presence of gas.
Okay, good to know those petrophysicists have some tricks up their sleeves.
Yeah.
Now, we've been talking a lot about interpreting these squiggly lines on logs, but I'm curious, are there any tools that give us a more visual representation of what's going on down there? Like, can we actually see those fractures,
You bet. That's where image logs come in.
image logs, so we can actually get pictures of the inside of a well bore?
Pretty much. These logs use some really fancy tools to create detailed images of the borehole wall, almost like taking an ultrasound of the Earth.
Wow. So we can actually see those fractures, the layers of different rock types.
Exactly. And we can even see signs of stress in the rock.
So it's like getting a peek behind the curtain, seeing the Earth's anatomy in all its glory. What kind of detail can we see in these images?
It's pretty remarkable. We can see natural fractures that were already there in the rock, as well as those tiny cracks called drilling-induced fractures that form as we drill the well.
Drilling-induced fractures. So we're actually creating fractures just by drilling the well.
Yep. And those drilling-induced fractures, they're really interesting because they tell us a lot about the direction of the stresses in the rock.
How so?
Well, those cracks, they tend to form in the direction of the maximum horizontal stress, basically the direction where the rock is being squeezed the hardest.
So by looking at the orientation of those cracks on the image log, we can get a sense of which way the stresses are pushing and pulling down there.
Exactly. It's like the wellbore itself is giving us clues about the forces at play deep underground. And knowing those stresses is crucial for planning our fracking strategy.
Right, because we want to create fractures that propagate in the direction of least resistance, basically following the path of those natural stresses, right?
You got it. That way, we maximize the effectiveness of our treatment and minimize the risk of creating unintended fractures.
So it's all about working with the Earth, not against it.
Precisely. We're trying to harness those natural forces to our advantage.
Now, in addition to those image logs, the chapter also mentions something called caliper logs. What can those tell us?
Caliper logs measure the diameter of the borehole.
The diameter, so basically how wide the hole is at different depths.
Exactly. Now, you might be thinking, why do we care about that? But it turns out that changes in that borehole diameter can actually tell us a lot about what's going on with the rock.
Okay, I'm intrigued. How does the size of the hole relate to all the rock properties we've been discussing?
Well, remember how we talked about well bore breakouts, those zones where the borehole wall kind of collapses inward a bit?
Right, those happen when the stresses in the rock are higher than the strength of the wellbore.
Exactly. And guess what? We can see those breakouts on the caliper log.
Really? So a breakout would show up as a wider section of the borehole on the log.
Yep. Because the rock has literally caved in a bit, making that section of the borehole larger. And on the flip side, if we see sections where the borehole diameter is smaller than expected, that could indicate the presence of those drilling-induced fractures we talked about earlier.
Because those fractures split the rock open,
Yeah.
making the borehole slightly narrower in those areas.
You got it. So the caliper log is like another piece of the puzzle, helping us confirm or challenge what we're seeing on those image logs.
Between those two types of logs, we're really getting a comprehensive view of the wellbore, aren't we? Its shape, any features that might indicate stress variations.
Precisely. And all that information, it's like gold when it comes to designing those fracking treatments, because we need to know where those stresses are highest, where they're lowest, so we can really create fractures that propagate in the right direction. That's how we maximize the stimulation of that reservoir.
So it's all about precision, targeting those sweet spots,
Right.
and making sure those fractures grow where we want them to grow.
Exactly. But even with all these amazing tools, we still need to be cautious. The subsurface, it's a complex environment.
I bet. What kind of challenges do we face when interpreting these logs and designing those fracking treatments?
Well, one thing to consider is something called mud filtrate invasion.
Mud filtrate invasion, what's that?
Remember how when we drill we use drilling mud to lubricate the drill bit. Well, sometimes that mud seeps into the surrounding rock.
Ah, so it's like the drilling mud is contaminating the very rock we're trying to measure.
In a way, yeah. That mud filtrate can actually mess with our log readings, making it harder to get a clear picture of the true rock properties.
So it's like trying to read a book through a smudged window. You can see the words, but they're not as crisp as they should be.
Exactly. So we need to account for that mud filtrate invasion when we're interpreting the logs.
So how do we clean the window, so to speak?
We use mathematical models to correct for that invasion. It's all very technical, but basically we take into account the properties of that drilling mud, how far it's likely seeped into the rock, and we adjust our readings accordingly.
Okay, so we're filtering out the noise to get a clearer signal. What other challenges are there?
Another important factor is environmental corrections. You see, those well logs, they're typically recorded at the temperature and pressure conditions downhole, which can be vastly different from conditions at the surface.
Right, it gets much hotter, and the pressure increases dramatically as you go deeper.
Exactly. So we need to adjust our readings to account for those differences. Otherwise, we might be getting a skewed view of the rock's true properties. It's like trying to measure a piece of metal that's been heated up. Its dimensions will change due to the temperature.
Right, so we need to calibrate our measurements based on those downhole conditions.
Oops, precisely. It's all about getting the most accurate representation of the rock's properties.
It's incredible how much goes into interpreting these logs and making sense of the data. Petrophysics is definitely a lot more complex than I initially thought.
It's a fascinating field. Those petrophysicists, they're like detectives using all these clues and their knowledge of rock physics to really paint a detailed picture of what's happening miles beneath our feet.
And that picture is what guides the entire hydraulic fracturing process, right?
Exactly. From choosing the right location to drill to designing those fractures to maximizing production, it all starts with understanding the rocks.
Now, speaking of designing those fractures, the chapter really emphasized the importance of understanding something called stress anisotropy. I know we touched on this earlier, but could you elaborate on why it's so crucial?
Sure. Stress anisotropy. It basically means that the stresses in the rock vary depending on the direction. It's not uniform. Think of it like squeezing a loaf of bread. It's much easier to compress it from the sides than from the top or bottom.
Ah, that's a great way to visualize it. So if the stress is higher in one direction than another, the fracture is more likely to grow in the direction of least resistance.
Precisely. And that's why we need to accurately characterize that stress anisotropy before we design our treatment. We want to make sure those fractures grow in a way that will most effectively stimulate that reservoir and maximize production.
So ignoring stress anisotropy could lead to some pretty big problems.
Oh yeah, definitely. We could underestimate the stress magnitudes, create fractures that grow in unintended directions, and ultimately end up with a less effective treatment.
So it's all about working with those natural forces in the rock, not against them.
Exactly. We want those fractures to grow where they're supposed to grow. No surprises down there.
Now, I know we've been focusing a lot on the technical side of things, but I'm curious about the practical applications. How does all this information actually get used out in the field? Like, do the engineers carry around these giant logs and try to decipher them while they're drilling?
Huh. That would be quite a sight. No, it's a bit more sophisticated than that. All of that well-log data gets fed into these really powerful computer models.
Okay, so it's like creating a digital twin of the subsurface.
Exactly. And those models, they help engineers design those fracking treatments. They use that data to determine the best location for the wellbore, how deep to drill, how long to make those fractures, even the type and amount of fluids to use.
So those logs are basically providing the blueprint for the entire operation.
Pretty much, it's a testament to how far technology has come and how crucial petrophysics is to this whole process.
Now, the chapter also got into some specific examples of how different log responses can be used to figure out rock properties. One that caught my eye was this discussion of using sonic logs to estimate those mechanical properties of a formation.
Oh yeah, that's a good one. Remember how we talked about those sonic logs measuring the speed of sound waves?
Right, and that speed tells us about the rock's stiffness. It's Young's modulus.
Exactly. And it turns out those speeds are directly related to other mechanical properties too, like Poisson's ratio. By analyzing those sonic log readings, we can actually calculate those properties, which gives us a much better understanding of how the rock will behave when we start fracking.
It's fascinating how something as simple as measuring the speed of sound can tell us so much about the rock's behavior.
Hmm.
And knowing those mechanical properties is crucial for designing those fractures, right?
Absolutely. We want those fractures to grow in the right direction, at the right speed, and effectively stimulate the reservoir. And those mechanical properties, they give us that insight. It's like having a cheat sheet for how the rock will respond to our treatment.
Okay, all of this is really starting to click. It's like we're slowly peeling back the layers of the onion, revealing all the complexity and the ingenuity involved in this process.
And it's all thanks to petrophysics, that science of understanding rocks and fluids. It's like we've got this secret decoder ring for the subsurface, allowing us to really unlock those secrets and access those valuable resources.
It's like we're speaking the language of the Earth.
I like that. We're definitely getting fluent in petrophysics.
We are. But before we get too carried away with the technical details, I wanted to bring us back to the big picture for a moment. Why should the average person care about all this?
That's a great question. I think it's important for everyone to have at least a basic understanding of where our energy comes from and how it's produced.
Hmm.
Hydraulic fracturing has become a major source of oil and gas, so understanding the science behind it can help us have more informed conversations about its benefits, its risks, its potential impacts.
So it's about empowering people to make informed decisions, regardless of where they stand on the issue.
Exactly. Whether you support or oppose hydraulic fracturing, understanding the science behind it is essential for having a meaningful discussion. We all rely on energy in our daily lives, so it's crucial to be informed about the technologies that provide that energy.
Well said. And I think our deep dive into petrophysics has certainly shed some light on the complexity and the nuance involved. It's not just a black and white issue. There's a lot of gray area.
Absolutely. And I think that's one of the most important takeaways from today.
Okay, so we've established that petrophysics is crucial for understanding those underground formations and for making informed decisions about fracking. But I'm curious about something we haven't really talked about yet. What happens after we create those fractures? How do we know if they've actually stimulated the reservoir the way we want it?
That's where production monitoring comes in. It's like we've set the stage, created those pathways for those fluids to flow, but now we need to make sure the show actually goes on as planned.
So we're not just walking away after we frack the well, we're keeping tabs on how things are going.
Oh, absolutely. We need to track how much oil or gas is coming out, at what rate, and for how long. We're constantly collecting data, measuring pressures, analyzing fluid compositions.
So it's like getting feedback from the reservoir itself, seeing if our fracking plan was a success.
Exactly. And based on that feedback, we can make adjustments, tweak our approach, and ultimately try to get the most out of those valuable resources.
So it's an ongoing process, not a one-time event.
Precisely. It's all about optimization, making sure we're doing the best we can with the resources we have.
This has been so insightful. But before we wrap up our petrophysics adventure, I wanted to touch on one more concept that's often mentioned in these discussions about fracking: formation evaluation. The chapter just briefly mentioned it, but can you explain what it is and why it's so important?
Formation evaluation. It's like putting together this giant puzzle.
Oh, how so?
We take all the data we've collected from the well logs we talked about, core samples, production data, and we use it to build this really detailed understanding of the reservoir's characteristics and its potential.
So we're not just looking at individual pieces of information, we're integrating them to get the big picture.
Exactly. It's about understanding the whole system, how everything interacts. We're trying to figure out things like what kind of rock is down there, how porous it is, what fluids it contains, and ultimately how much oil or gas we can realistically extract.
It sounds incredibly complex.
Yeah.
What are some of the challenges involved in formation evaluation?
Well, one of the biggest challenges is dealing with uncertainty. Remember, we're working in this world that's hidden miles beneath the surface. We can't actually see it directly, so we have to rely on these indirect measurements, interpretations, and there's always a margin of error involved.
So it's about managing that uncertainty and making the best decisions possible with the information we have.
Exactly. And that's where the expertise of those petrophysicists and those reservoir engineers really comes in. They use their knowledge of rock physics, fluid flow, all those complex things to interpret the data, assess those uncertainties, and make recommendations about how to proceed.
And in the context of hydraulic fracturing, formation evaluation plays an even more crucial role, right?
Oh, absolutely. We need to make sure that we're fracturing the right zones, that our fractures are actually propagating as intended, that we're not creating any unintended pathways for those fluids to migrate. Formation evaluation helps us minimize those risks and maximize the potential of the reservoir.
Okay, so it's like the final check, making sure we've done our homework before we start fracking.
You got it. It's an essential step that really integrates all that data and gives us a comprehensive understanding of what we're dealing with. And that understanding is what allows us to make those informed decisions about how to develop our energy resources safely and efficiently.
It's pretty amazing how much information we can get from those well logs and all those other data sources. It's like we're piecing together a giant underground puzzle.
It really is. And petrophysics, well, that's the key that unlocks all those secrets. It allows us to really see into the Earth, to understand its complexities, and to harness those vast resources that power our world.
This has been such an eye-opening conversation. I feel like I've learned so much about the science and the engineering behind hydraulic fracturing, as well as the challenges and the considerations involved. It's definitely a lot more nuanced than I initially thought.
It's definitely a complex topic, but I'm glad we could shed some light on it today.
Me too. Now, before we wrap up, I wanted to touch on one more question that often comes up when discussing fracking. The potential for induced seismicity, or what some people call man-made earthquakes. The chapter didn't really go into detail about this, but I'm curious to get your take on it.
It's definitely a valid concern. While fracking itself doesn't usually cause felt earthquakes, there is a connection between oil and gas operations and induced seismicity in some cases.
Okay, so it's not the fracking itself that's the problem.
In most cases, no. The actual process of creating those fractures, it doesn't usually generate enough energy to trigger significant seismic events. However, the disposal of wastewater from those operations, that's a different story.
Wastewater disposal. What does that have to do with earthquakes?
Well, that wastewater often gets injected back into deep underground formations, right? And when we inject large volumes of fluids like that, it can actually change the stresses on those pre-existing faults, those natural breaks in the Earth's crust.
Ah, so it's like we're upsetting the delicate balance down there.
In a way, yeah. And if those stresses change enough, well, it can potentially trigger an earthquake.
So it's not the fracking itself, but rather what we do with the wastewater afterwards that can sometimes cause problems.
Right. It's important to note that the vast majority of those disposal wells, they operate without any issues. But there have been some cases where that injection of fluids has been linked to an increase in earthquakes, particularly in areas with pre-existing faults that are already close to failure.
So it's about understanding the geology of the area and making sure we're not injecting wastewater into zones that are particularly prone to seismic activity.
Exactly. Careful planning, monitoring, and regulation are key to minimizing those risks.
Okay, so it's a complex issue, but one that we're becoming more aware of and taking steps to address.
Absolutely. The oil and gas industry, along with scientists and regulators, is constantly working to improve our understanding of induced seismicity and to develop technologies and practices that will help minimize those risks.
So it's a reminder that with any technology, especially one that interacts with something as complex as the Earth's subsurface, there are always potential risks and uncertainties.
Right. We need to be aware of those risks, mitigate them to the best of our ability, and always strive to do better. It's all about finding that balance between energy development and environmental protection.
Well said, and I think that's a perfect note to end on. This has been an incredible journey into the world of petrophysics, hasn't it?
It really has. I'm so glad we could share this deep dive with everyone.
Me too. It's been fascinating to explore how we use science and technology to unlock those energy resources that power our world. And I think we've all learned a lot about the complexities and the nuances involved.
I hope so. And to all our listeners out there, keep exploring, keep asking questions, and never stop learning.
Thanks for joining us today. Until next time, stay curious.
Wow, what a journey this has been. I mean, really, we've gone from the squiggly lines on a log to understanding how to pinpoint the best spots to frack.
And how to avoid the not-so-good spots,
Yes.
right? Like those clay-rich zones we talked about.
Right, those mirages in the desert. It's incredible how much information we can extract from these measurements.
It's like we've learned a whole new language, the language of the Earth.
Exactly. And it's all thanks to Petrophysics, that secret decoder ring.
Petrophysics, it's the key to understanding this hidden world beneath our feet.
Okay, so we've talked about how to find those sweet spots for fracking, but what happens after we create those fractures? How do we know if they're actually working the way we want them to? Are we just hoping for the best? Huh. No, definitely not hoping for the best. That's where production monitoring comes in. Think of it like this. We've set the stage, created those pathways for the oil and gas to flow.
Okay, so we've built the roads, so to speak.
Exactly. But now we need to make sure the traffic is flowing smoothly, that there are no bottlenecks or roadblocks.
So we're keeping an eye on how much oil and gas is coming out of the well, how quickly it's flowing.
Right. And we're also looking at things like the pressure of the well and the composition of the fluids that are coming out. All of this information helps us to understand whether our fracking plan was a success and if we need to make any adjustments.
So it's like getting feedback from the reservoir itself.
Exactly. We're constantly listening, monitoring, and tweaking things to optimize production. We want to get the most out of those valuable resources while also minimizing any potential impacts.
Speaking of impacts, I think it's time we address the elephant in the room. the environmental considerations surrounding hydraulic fracturing. It's a topic that often generates a lot of debate, and I'm curious to hear your perspective.
Yeah, it's definitely a complex issue with valid concerns on all sides. I think it's important to be upfront about the potential risks, but we also need to acknowledge the advancements that have been made in reducing those risks.
So, what are some of the biggest environmental concerns when it comes to fracking? I know people often talk about water contamination and earthquakes.
Right, those are two of the main concerns that come up, and they're legitimate concerns. When we're injecting fluids into the earth, there's always a risk that those fluids could migrate into places we don't want them to go, like underground aquifers or surface water sources.
And those induced earthquakes, are those a real risk too?
There have been cases where wastewater disposal, that's the process of injecting that used fracking fluid back underground, has been linked to an increase in seismic activity. But it's important to note that this doesn't happen everywhere, and the industry is working hard to better understand and manage those risks.
So it seems like there's a lot of research and development going on to make fracking safer and more environmentally friendly.
Oh, absolutely. There have been huge advancements in things like wellbore integrity, using less water in those fracking fluids, and even recycling and reusing that water. And when it comes to induced seismicity, we're getting much better at identifying areas that are more susceptible to those risks.
So it's really about acknowledging those risks and taking proactive steps to address them. It sounds like the industry is making progress, but there's always more to be done, right?
Definitely. It's a continuous process of improvement. And I think that's one of the key takeaways from our conversation today. Petrophysics isn't just about optimizing production, it's also a crucial tool for understanding and mitigating those environmental concerns.
Right. It's about using science and technology responsibly.
Exactly. We need to find that balance between harnessing these valuable resources and protecting our planet.
Well said. It's been an amazing journey into this hidden world beneath our feet, hasn't it?
Yeah.
We've gone from those squiggly lines on a log to a much deeper understanding of hydraulic fracturing and all its complexities.
It has been a really interesting journey. I'm glad we could explore this fascinating world together.
Me too. Thanks for joining us on this deep dive into petrophysics. We hope you found it as enlightening as we did.
I hope so too.
And to all our listeners out there, keep those brains buzzing, keep asking questions, and we'll catch you on our next deep dive.